let's now switch to English. And I would like to start, given that I solved the technological, hopefully, I solved the technological problems, I would like to start with some examples on the PC that I would have liked to show you yesterday, but we couldn't. So let me start just with some experiments, because I think it's important in statistics not just to look at the formulas, but also to make some experiments. Because as I said, statistics is a very practical science, but of course we don't have to lose the practical meaning, and the only way not to lose the practical meaning is to practice. So let me start with just some examples. This is not an exercise, it's just a demonstration, a practical demonstration of some concepts that we studied yesterday. I think it is useful for you if you try to make the experiments with me. So if you have the personal computer, I suggest that you try, I will try to be slow, and I suggest that you try to make the experiments with me. So first of all, let me start R, and to increase the font size. Okay, now let me start by generating Gaussian data with the first procedure that I explained yesterday. So just using the R functions. And you can do it by doing, for instance, let's call the variable PR1. You can decide whatever name you prefer. And let's assign to this variable a generation. I told you yesterday the instruction is rnorm, generation of, let's say, 100 data. And if you don't put any more specification, it generates from the canonical distribution, meaning the mean value is 0 and the standard deviation is 1. You see, generation is already done. Now let's have a look at the graphical representation. So plot PR1, and let's use a line to plot it. Again, what is this? It's a graphical representation of Gaussian data that have no memory. And this is the picture. You see, this is data that are just wandering around the mean, fluctuating around the mean randomly. The mean is 0. You can just put in evidence the mean by writing AB line H equals 0. So this is the mean. We generated just 100 of data, and therefore you see that that there is some sample uncertainty. What do I mean? The distribution is supposed to be symmetric. It means that you should have the same amplitude above and below the mean. Here you see that it's not like so. If you look at the data, it seems that you see the scale of the y-axis. It's ending at -2, but is extended until 3 over the positive direction. So it means that the data are really not really symmetric. And let's compute the average to see if they are symmetric, to see what is the value of the average. And you see that it's positive. It would be supposed to be 0, but of course, when you generate just 100 of data, you get some uncertainty. It's called sample uncertainty, meaning that when you have a small sample size, a few data, then there is some uncertainty in the statistical inference. And this is even more evident if you generate just 10 data and you compute the mean. Yeah, it's always positive, not more positive than before. Let's have a look at the graph. Here it is, and let me show the mean. You see, even in this case, the distribution is not really symmetric. Now let's try with a greater sample size. Let's try with 1000. This is the plot, and let me show the mean. You see that Okay, it's more difficult to read this graph. It's more difficult to read a graph when you have a lot of data, but in this case it seems that the distribution, at least if you look at the scale of the ordinates, they are extended, they are symmetric, -3, 3. And let's try to compute the mean value. You see that it's closer to 0, it's almost 0. And let's compute the standard deviation. Let's do it square root of variance of PR1. You see, basically it's 1. Now, it's interesting to compute the probability density for this data. Of course, we expect it to be Gaussian, and we expect it to be symmetric. First of all, let me refer to a smaller sample size, because otherwise it's difficult to read the graphs. So let me refer to a sample size of 100, and the plot is this one. Plot is this one now. And how to compute the density for this data? Because this is a continuous variable, and therefore it's not immediately clear how you can compute the density. We studied yesterday how to define the density, and you may remember that we made reference to very small intervals along the range of definition of the variable. And in fact, this suggests us a way to compute the sample density, sample probability density for a series of numbers. What you should do is take along the x-axis the range of definition of the variable. In this case is -3, 3, I think, -2, 2, sorry, doesn't matter. Let's keep -3, 3, just to give you an example. Here it's 0. So a way to compute the sample density would be to discretize the range in small intervals. Like, let's divide it in 50 parts. In my case, I can't write 50 small intervals. Let's just take 1, 2, 3, 4, 8 of them. Okay? And of course, these limits are defined. Here it's -275, -2.5, no, sorry, because it's 3, so it's divided by 4, so it's, okay, let's say that, too complicated, let me put -3 here. So this is 1, 2, -1, -1, -2, and this is 1, 2, okay? And let's put a -4 here and a 4 here. Now you have these intervals whose limits are defined, and you can compute how many observations fall within each of them. And in this case, you get what? You get indeed a frequency of the times that any number falls within each interval, which is proportional to the probability density. Why proportional? Because then you have to divide for the size of the interval. Once that I computed the number of times that each observation falls inside each interval to get the probability density, as I explained yesterday, I have to divide by the size of the interval. So, if you count the number of times, like this one, let me say this one, here, here, I expect it to be symmetric, so I know it's symmetrically, and this is the number of times, the number of observations that fall within each interval. You divide by the delta x, and finally you get an estimate. of the probability density function. This is a way to compute, to estimate what is called the sample probability density. And this can be done by R. Let's try to use an R function to do that. And the name of the function is density. So let's plot it. Plot, open round parenthesis, density of PR1. And let's use a line to draw the plot. And let's look at the result. You see, this is the instruction. Plot density. PR1 type is L. This is the result. And indeed, it's pretty symmetric. And it's pretty similar to the shape of a Gaussian distribution. And first of all, there are options here. I used default options. There are options for the computation of the density and also for drawing the plot. And in particular, for computing the density, you can specify how many intervals you want. And looking at this density, you see again that it's symmetric, pretty symmetric. And if you look also at the area below the curve, you understand that it's close to 1. We will compute the area later on. But you see that the maximum ordinate is 0.35. The base of the curve is about 6. So if you compute 6 times 0.3 is about 2. And if you 2, it would be the rectangle that includes the bell. If you divide by 2, it's more or less 1. And we will compute anyway the area below the curve. And let me now be more detailed in this function, about this function density. Density gives back an output which is more detailed than what I just plotted. And let's see. Let's call a variable PR2 that collects the output of density. And let's see what is included in this output. It's a list. PR2 is a list. And if you want to see what's included in the list, you see that there are a lot of things. I'm not going into details. What is important for us is just X and Y. X and Y allow us to draw the graph. For instance, if I want to plot it, I can also use this instruction, plot PR2 X, PR2 Y, type equal line. And I get, sorry, I forgot the commas. And you get the same result. This is probability density. You might be interested in getting the cumulative density. The cumulative density to see also the shape. And if you want to plot the cumulative density, what you have to do is just to substitute PR2y, the ordinates, with the cumulative sum. Cumulative sum is cum sum. Sorry, I made a mistake. Let me explain what is the cumulative sum. It's intuitive what is. If you want to compute the cumulative sum of this vector, 1, 2, 3, 4, you get this result. So you can understand what is the cumulative sum. It's the integral. You see 1 plus 2 gives 3, 3 plus 3 gives 6, 6 plus 4 gives 10. Now, let's try once again to change, to correct the mistake in the previous instruction, and let's now try to plot the cumulative sum of the probability density depending on x, and we should get the cumulative density. Let's see the result, and you see that indeed what you are getting is a cumulative density. The only thing is that if you look at the ordinates, you can't understand the scale. Because it seems that the scale, we would expect a scale between 0 and 1 for the cumulative density. So what is the reason why the scale is not comprised between 0 and 1? It's quite easy to understand. Because the probability density was comprised, I think, was 0.3 maximum ordinate. So you need to rescale it to get the cumulative density, because if you sum all these ordinates, what you get is basically the cumulative density that is multiplied by the delta x. Let me think about it. Let me think about what I'm saying, if it is correct. Because, of course, you get here, the area should be 1, so to get the area, let me think, what is it divided by? Okay, first of all, let's compute delta x by r, and then we have to decide if we have to multiply or divide by it to rescale the ordinates. Let me compute delta x. And first of all, in order to understand how to compute delta x, I have to know how many intervals are used. Because of course, in order to get the value of delta x, you have to divide the range of the variable by the number of intervals. Okay? So the range of the variable, we can compute it by just computing. Let me clear the screen. Just by computing the maximum value of PR2x. And I have to subtract the minimum value of PR2x. This is the length of the range. Basically, it matches what we are expecting. From -3 to 4 is about 7. It's 6.8. This is the range. Now, how many intervals are used to compute the density? The intervals, we can see how many they are by looking at the length of PR2x, for instance. The length is 512. So let me compute now the delta x divided by length PR2x. This is the delta x. Okay. Now let me try with the cumulative sum of PR2y, which, now let me say, not the sum of PR2y, which is 75, and let me multiply it times this. you see we got 1. So basically, by multiplying the sum of the ordinates for the delta x, I get what I wanted to estimate, which is the cumulative density function of the variable, which now I'm going to plot. So I'm copying this instruction here. And then I go to plot this one. Let me see if it is correct. It seems yes. Okay, this is my cumulative density function. I go back to the instruction. So basically what I did is to take the ordinates of the density, to take the cumulative sum of the ordinates, then I have to rescale it by multiplying it times delta x, because you know, you remember yesterday the integral. Yesterday we said that I'm trying to explain why I have to multiply times by delta x. Yesterday we say that the cumulative density function is given by the integral between, in this case is -4 to about +3, if I well remember, of the density times the x. So this is the reason why here I have to multiply by delta x if I want to get the cumulative density function. So basically with this instruction I am plotting the x variable, which is just given by the sequence of the delta x, and the cumulative sum of the ordinates of the densities times the delta x. And the delta x is just the difference between maximum and minimum divided by the number of intervals. And indeed, if I do so, what I get is the cumulative distribution of the variable, and if I draw a vertical line on the average, let me draw it. B equals 0. You see that it's pretty symmetric around the average, as we are expecting. This is just a procedure for simulating data plus some graphical techniques for visualizing what we did. I told you there is a second procedure for simulating which passes through generating outcomes from a uniform distribution. This is what R does. He generates first outcomes from a uniform distribution and then compute the inverse of the probability distribution. If you look at your notes yesterday, there are 2 steps in this second simulation procedure. First, generation of outcomes from a uniform distribution, and then computation of the inverse of the normal distribution for each outcome from the uniform distribution. So let me do it. First of all, the uniform distribution. Let me write here 1 is equal to R unif. This is the routine to generate from the uniform distribution 1. And if I don't specify any more argument for this function, it means that the range of definition is between 0 and 1. That is what we want to get, indeed. So this is generation from a uniform distribution. Let's see what the result is. If you look at the plot, you see that the outcomes are comprised between 0 and 1. And by just looking at the plot, we cannot distinguish clearly that the distribution is different than before. Indeed, if you make a comparison you would see some difference. Let me try to show you. If I generate now PR2 equal R norm, probably the scale. Okay, but anyway, 100. And now I plot it. What I did with this dev new instruction is to open a second graphic screen with this dev new instruction. Let me plot on the second graphic screen here too. And now let me compare the two series. It's not easy to compare them because you know the scale is different, but let me try to do that. I have to shrink the window. Let me put it here. And let me get back to the previous one. Let me shrink it. You see, these are the two series. Let me just make okay, this way they are about the same size. On the left you see outcome from a uniform distribution, on the right outcomes from a Gaussian distribution. Indeed you see that the shape is different. It's different why? Because the Gaussian distribution has the outcomes that are closer to the mean. Instead, for the uniform distribution you see that the outcomes are more randomly displaced, let me say that. But it's not easy to see the difference. And which graph should we draw to see the difference? The density. So let's try to plot the densities now. And I think that we can now close the second graphic device and let me write the density of PR1, which is the outcomes from the uniform. And this is the density. And you see that we get what we were expecting, meaning a flat density. It's not really flat because here we have a reduced sample size, but it's quite flat. Let me now try with a longer sample size so you can really 10,000, you can really get, you see, it's flat. Instead, if I look at the density of the Gaussian, again, you see the difference. Okay, so let me go back to the uniform distribution, and let me go back to the size of 100. And now, let's go to the second step to generate outcomes from the Gaussian distribution. I generated the outcomes from the uniform. Now let me write PR2, which are outcomes from the Gaussian, is equal to Q norm. Q norm means inverse of the normal distribution, Q norm of PR1. It computes the inverse of the normal distribution for each outcome from the uniform. And let's see the results. First of all, the density. It's Gaussian. You see? It becomes more evident if you use a sample size of 10,000, and then you compute again the inverse, and then let's plot the density. You see, I changed the sample size to 10,000, and now let's see. It's a quite nice bell. So, what I did, basically, is for each outcome from the uniform, which is comprised between 0 and 1, I assume that these are probabilities that are uniformly distributed, and then I compute the inverse of the Gaussian for each probability. And in doing so, I indeed get outcomes from the Gaussian, because probabilities are uniformly distributed, but for each probability, the Gaussian distribution gives outcomes that are Gaussian, not more uniform. And I don't remember what I wanted to say, but I will remember. Okay, what I wanted to say is quite important. It's a detail about terminology. Why the function in R is called Q norm. Q stands for quantile. And this is a terminology that is important that you learn. For an assigned probability, the inverse of a given probability distribution, which gives to you the value of the variable, is called quantile. So let me be more detailed. The probability distribution gives you the probability of, for instance, let's refer to the cumulative, the probability that capital X is lower or equal than small x is given by the capital F of small x. So it means that in a probability distribution in general, you enter with a given value for the variable that you are modeling, like river flow, and you get an estimate of the probability, in this case not exceedance. So the probability distribution starts from the variable and gives you the probability. If you invert the distribution, you expect that you give as input a probability and you get back a value for the variable. So let me write it. If you take f minus 1, the argument then is a probability, and this gives back to you the capital X. And this, the lowercase x. And this is called, when you compute the variable value using a probability distribution, this is called quantile. In Italian it's quantile. This is important that you know, because the word quantile, you heard it many times, so it's very important that you understand what it means. And therefore, the R function is called Q norm, quantile from the normal. Good. Okay, now let's talk about correlation. We learned yesterday what correlation is. And it's very simple. In order to compute the correlation, let me write back the formula for computing the correlation coefficient. And its rho depending on L is equal to 1 divided by n minus L sum from, I think yesterday I used I equal to, I think it was I1 extended to n minus L divided by sigma squared x of, it was x I plus L minus b x times x I minus b x. Yeah, I would say it's correct. This is the formula for computing the correlation coefficient. Now, as I said yesterday, if you draw a function that depicts an histogram, a graph that depicts the value of the correlation coefficient against the L value, I said that you get something called autocorrelation function. And you can compute it in R by writing just ACF. This is the function. Let's compute it for PR2, which is a Gaussian series that has a sample size of 10,000. And let's look at the resulting graph. Okay, you see what's going on here. First of all, you have that for L equal to 0, you get 1. Fine, this is what we were expecting. Let's forget about the blue lines around the 0 value. Let's forget about them. And what you get here is a sequence of values. You see, they are very close to 0. The values are here. You see these bars. They are almost all included within the blue lines. Let's forget about the blue lines. I will explain later what they mean. But in any case, you see that the values for the correlation coefficient are very close to 0. This is what we were expecting, because we generated data that have no memory. We just picked up outcomes from a distribution. Just for comparison, let me refer to the time series of the Po River at Ponte Lago Scuro. Ponte Lago Scuro is conventionally adopted as the closure section of the Po River. It is located about, I don't remember how many kilometers upstream from the delta, but it's quite upstream.